Dear students, I welcome you all to this problem solution series in digital electronics. I am solving the problems from the book Digital Design by Maurice Mano and Michael Sileti. So in this video, I am solving the problem number 6.19 from the chapter number 6. The problem is the flip-flop input equations for a BCD counter using T flip-flops are given in section 6.4. Then we are asked to obtain the input equations for BCD counter that uses JK flip-flops in part A, and in part B we have to use D flip-flops. So we have to then find out the input equations for the JK flip-flops and the D flip-flops. To design the same BCD counter, we have to now use JK flip-flops, and we have to find out the J and K input equations and D flip-flops. For that also we have to find out the input equations for the D flip-flops. In the third part of the problem, we have to compare the three designs to determine which one is the most efficient. So from the book we have got input equations TQ1. That means for the first flip-flop we can directly connect the T input to the logic 1. So for the second T flip-flop we have to use this equation. That means the fourth flip-flop complemented output will be multiplied through a AND gate with Q1 output. Q1 is the normal output of the first flip-flop. For this third flip-flop we have to multiply the second flip-flop output with first flip-flop output, and the AND gate output will be connected to the third T flip-flop input. And for the fourth T flip-flop input, this is T8 is the fourth flip-flop that is carrying the most significant bit. This T8 represents the input T of the fourth flip-flop that will carry the most significant bit. So here we can see that we have to use one AND gate and one OR gate, one another AND gate. That means here we have to use two AND gate and one OR gate. So first of all, let us write down how many gates we have to use. Number of AND gates I am writing here because this will help us to determine which is the efficient one. Okay, so number of AND gates is equal to here 1 AND gate, 2 AND gate, 3 AND gate, 4 AND gate, 4 AND gate. So and the number of OR gates is equal to, this is only 1. Okay, so here you can directly connect to the logic 1. Okay, so total number of gates is equal to 4 plus 1, it will be 5. Okay, we need 5 total number of gates for designing this BCD counter using T flip-flop. So now let us go to our first part of the problem. So we have to design the same BCD counter using JK flip-flops. Now we have to make the state table first, and from the state table we will find out the input equations for the 4 JK flip-flop inputs. At the same time we can also find out the respective D inputs, okay, for the D flip-flops, because the present state and the next state will be the same. So state table for the BCD counter, this is nothing but a synchronous counter. Okay, so here we'll have present state, then we have next state, and then we have to find out the flip-flop inputs. Suppose the present state outputs are A8, A4, A2, A1. Here we have written as 8421 because it is a BCD counter. Okay, so in the case of BCD we write in this form. Suppose for the next state we represent it with, suppose A 8, and this n is for the next state, BA 4n, then we have A 2n and A 1n. Suppose this n is for the next state. Then we have to find out the flip-flop inputs. So for 4 JK flip-flops, here we'll have JA8, KA8, JA4, KA4, then JA2, KA2, then JA1, KA1. So for all the 4 flip-flops, the J and K inputs we have to find out here. So in the second part we have to find out for the D flip-flops. Okay, so here let me write down DA8, DA4, DA2, DA1. So a BCD counter starts from 0000 to 1001. That means it counts from 0 to 9. So it has 10 number count. Starting from 0000, then 0001, in this way up to 9. Okay, so up to 9 we have to find out because it is a BCD counter. Okay, so 1 2 3 4 5 6 7 8 9 10. So we can count 10 number of pulses using these states. So for the present state 0000, the next state will be 0001 because it is a counter. So if we assume it to be a up counter, so it will increment by 1. So here we'll have 0001. Here we have 0001 1. So you have to make this 2. So 2 is 0010, and similarly so on. So after 9 we have to go back to 0000. We have to use the excitation table of JK flip-flops for finding out the JA and KA inputs. So here we have A8, A8N, that means the next state. Okay, so here we have to fill out for JA8 and KA8. So using these two first column and this fifth column, we have to find out this JA8 and KA8 values. Okay, so using the excitation table, we know that whenever we have present state is equal to 0 and the next state also 0, the J and K inputs are 0 and don't care. So similarly here also 0 0. So here we'll have 0 and don't care. So 0 don't care, 0 don't care, 0 don't care, 0 don't care condition, 0 don't care condition, 0 and 1. So for 0 and 1 we'll have 1 and don't care. So 1 and 1 means don't care 0. Okay, so 1 and 0 means don't care 1. Now we have to find out for JA4 KA4. So this is the present state, second column, and the sixth column is the next state. Okay, so here we have 0 0. So here we'll have 0 don't care, 0 0 again, 0 don't care, 0 don't care, 0 and 1. 0 and 1 means it is 1 don't care, 1 1 means don't care 0, 1 1 means don't care 0, 1 1 means don't care 0, 1 0 means don't care 1, 0 0 means 0 don't care, 0 0 means 0 don't care. Okay, so we have got the inputs for this third flip-flop, that is JA4 KA4. Now we have to find out the J and K inputs for this second flip-flop. Similar process. So 0 and 0 will have 0 don't care. Okay, so 0 and 1, 1 don't care. So 1 and 1 don't care 0. So 1 and 0 don't care 1. So 0 0 0 don't care. Then we have 0 and 1, 1 don't care. So next we have 1 and 1, so don't care 0, 1 and 0, don't care 1. Now again we have 0 0, so 0 don't care. Then we have 0 0, so 0 don't care. Then we have to find out the least significant bit flip-flop, that is the first flip-flop that will have the inputs JA1 and KA1. So we have to see this fourth column and this eighth column, that is fourth column is the present state and the eighth column is the next state for this lowest significant bit flip-flop. 0 and 1. 0 and 1 means 1 don't care. 1 0 means don't care 1. 0 1 means 1 don't care. Then 1 0 don't care 1. 0 1 means 1 don't care. Don't care 1. 1 don't care. Then don't care 1. 1 don't care. Don't care 1. So we have got all the JA, KA inputs for all the 4 flip-flops. This is for part A. And for part B, we have to again find out the D inputs of all the flip-flops. That is, now we have to consider this first column for present state and fifth column for the next state. And we have to find out the respective D input. So for the D flip-flop, we have 1 input and 1 output. Okay, so to make the next state 0, we have to put the 0 value in DA8. So whatever be the value here at this fifth column, it will be the DA8 column. Okay, so we'll have 0 0 0 0 0 0 0, and we have 1 and 1 and 0. This is the fourth flip-flop. So for the third flip-flop, we'll have this sixth column will be same as this DA4 column. So here we'll have 0 0 0 1 1 1 1, 0 0 0 1 1 1 1. Then we have 0 0 0 0 0 0. Now we have to find out for the second D flip-flop. So this column will be same as this seventh column. That is 1 2 3 4 5 6 seventh column. Okay, so this a to n, that is the next state of this second flip-flop, will be equal to this input of the second flip-flop. So here we'll have 0 1 1 0 0 1 1 0 0 0 0 1 1 0 0 1 1 0 0 and 0. Similarly, for this first flip-flop, this input will be equal to this next state output. Okay, so here we'll have 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. Now we have got this state table for the BCD counter that is containing this input equations for JK flip-flop as well as for the B part of the problem. So we have to find out these D inputs. So these D inputs are equal to respective these columns. Now we will find out the expressions for JA, KA for all these four flip-flops, and then after that we will find out the expression for this DA, DA8, DA4, DA2 and DA1. So let us find out. So part A, we have to find out the expression for JA, K map for JA8. So here we'll have a 4 variable map because we need 4 variables for a BCD counter. So the 4 variables are A8, A4, A2 and A1. Okay, so A8, A4, A2 and A1. So here we'll have a 4 variable map. So this K map is similar to the previous problems. So 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. These two rows are A8. These two rows are A4. Okay, these two columns are A2 and these two columns are, that means second and the third column are for A1. Here we have to fill up the values of JA8. So for JA8 we have, these are the values. Okay, because these numbers are in serial order, so directly we can put this value serially at this map. So here we'll have 0 0 0 0 0 0 0. Then we have 1, don't care, don't care. 1, don't care, don't care. So these are the remaining states, unused states of this BCD counter. Okay, so here we'll put don't care conditions. Okay, so all these remaining states will be the don't care conditions. So how we can combine? There is only 1 so we will have only one term. So here we'll have JA8 is equal to, from this term we'll have, this is A4, A4. There we have 1 so A2, A1. So this is the expression for JA8. Now let us find out for KA8. Therefore, K map for KA8. So similarly, we have to find out the K map for KA8. Okay, so here we have this 4 variable map again for KA8. So now we have to fill up this 4 variable map with the KA8 values. So for KA8 we have this don't care, don't care, don't care, don't care, don't care and 0 1. Okay, so here we'll have don't care, don't care, don't care, don't care, don't care, don't care, don't care. Then finally we have 0 and 1, 0 and 1. So here also we'll have don't care conditions because these are the unused states. Okay, so how we can combine? So we can combine like this. So there will be only one term. So therefore KA8 is equal to, so from this combination we will get this A4 and A8 will be cancelled, and from these two row we will have A1. So KA8 is equal to A1. Okay, so we have got the expression for JA8 and KA8, and similarly we have to find out for JA4, KA4, K map for JA4, JA4. So here we'll have a 4 variable map. So now we have to fill up this K map with the values of JA4. So JA4, the values are 0 0 0 1, then don't care, don't care, don't care, don't care, 0 0. So let us put these values 0 0 0 1. Then we have don't care, don't care, don't care, don't care. Okay, Next we have 0 and 0, 0 and 0. Then these the remaining are don't care conditions because they are the unused states. Okay, so here we'll have only one term. This is the only one. So we can combine like this. So here we'll have JA4 is equal to, so from this term we'll have A2 A1, A2 A1. Now let us find out the K map for KA4. So here we'll have another 4 variable map. So these two rows are A8, these two rows are A4, these two columns are A2, these two columns are A1. Okay, now we have to fill up this K map with the values of KA4. So for KA4 we have this one. Okay, so don't care, don't care, don't care, don't care, then 0 0 0 1, don't care, don't care, don't care, don't care, don't care, don't care, 0 0 0 1. Then we have don't care, 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 don't care. So how we can combine? So this will be the only one term. So here we'll have KA4 is equal to, so from this combination we'll have A2 A1, A2 A1. Okay, so we have got the expression for KA4. Okay, now we will find out the expression for JA2 and KA2. K map for JA2. Here we'll find out K map for KA2. So for JA2, here we'll have a 4 variable map. So we have to fill up this 4 variable map for JA2 with the values of JA2 this column. So now we have to use this JA2 column values. Okay, so 0 1 don't care, don't care, 0 1 don't care, don't care, 0 1 don't care, don't care, and 0 0. So the remaining are the don't care conditions because they are the unused states. We can have only one combination. So for this term we'll have JA2 is equal to, so here we have A8 bar for this two row, A8 complement into, so from this two column we'll have, this is A1, A1. So we have got the expression for this JA2. Now for KA2, here we'll have another 4 variable map. So here we have to fill up with the values of KA2. So for KA2, we have don't care, don't care, 0 1, don't care, don't care, 0 1, don't care, don't care. Don't care, don't care, 0 1, then don't care, don't care. All the remaining are the don't care conditions. So here we can combine like this. Okay, so KA2 will be, so from the row side all will be this A8 and A4 will be cancelled because it is covered all the 4 rows. Okay, and from these two column we'll get it is A1. KA2 is equal to A1. Okay, so we have got the expression for KA2. Now let us find out the K map for JA1. So for the first flip-flop that has the lowest significant bit. Okay, so here we'll have another 4 variable map. So we have to put the JA1 values in this 4 variable map. So JA1 column is this one. So 1 don't care, 1 don't care, 1 don't care, 1 don't care, all are 1 don't care. 1 don't care, 1 don't care, 1 don't care, 1 don't care, 1 don't care. So here we do not have any 0, so the complete table we can take JA1 is equal to 1 because it has covered all the 4 rows and 4 columns. So here we have JA1 is equal to 1. That means we can directly connect the logic 1 value to this JA1 input. And K map for KA1. So here we'll have another 4 variable map. So here we have to fill up with the ka1 values. So for ka1 we have this don't care one, don't care one, don't care one, don't care one, and don't care one. Don't care one, 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 and the remaining are the don't care conditions. Okay, so we can cover all the table, all the 4 rows and the 4 columns. Therefore ka1 is also equal to 1. Now we have got the expression for ja8 ka8. Okay, ja8 ka8. Then we have found out ja4 ka4, then ja2 ka2, ja1 and ka1. So we have got the expression for all the 4 flip-flops. Therefore we have got therefore number of required AND gates is equal to, so here we have, this is one AND gate we can use here. So here we have to use one AND gate, 3 input AND gate. So this is another 2 input AND gate, 2 input AND gate, 2 input AND gate, and this directly we can connect from the first flip-flop output, normal output, to this ka8 input. Okay, we need not to use any gates for this a1 and 1 1, because directly we can connect to this logic level 1 and 1, and directly we can connect this ka8 input port to the first flip-flop or the least significant bit flip-flop output, normal output. So here we have to use 1 2 3 4 AND gates, and the number of required OR gates equal to 0. Therefore total number of gates required is equal to 4. So in the previous case we got that we required 5 total number of gates. Okay, now let us go to our second part of the problem, part B. So in the second part of the problem we have to find out the expression for DA8, DA4, DA2 and DA1. Okay, so we have to again make K-map for DA8. So here also we'll have 4 variable map. These 2 rows are A8, A4, A2, A1. Therefore here we'll get the expression for DA8 equal to, so we have to put the DA8 values from the state table. So here we have DA8 values are 0 0 0 0 0 0 0, then 1 1 0, 0 0 0 0 0 0 0, 1 1 0, 1 sorry 1 1 and 0, then all the remaining are don't care conditions. So this will be one term and this will be the second term. So from this term we'll have, this is a8 into, from these 2 column we'll get a1 bar, a1 complement, plus from this term we'll get, this is a4, and from this column we'll get a2 a1. Okay, so we have got the expression for this. Now we'll find out the expression for DA4. K-map for DA4. So here also we'll have a 4 variable map. So we have to fill up this K-map with the values of DA4. Okay, so DA4 we have 0 0 0 1 1 1 1, then 0 0 0, 0 0 0 1 1 1 1, then 0 0 0, then these are the don't care conditions. Okay, so how we can combine? So suppose this will be one term, then this will be suppose second term, and this will be the third term. Okay, so therefore we'll have dA4 is equal to, so from this term we'll get A4, A4 and A2 complement, A2 complement, plus from this term we'll get A4, so A1 complement, A1 complement, plus from this combination we'll get, this is A4 complement, A4 complement into A2 A1, A2 A1. If we further want to simplify it, so we'll get A4. If we take these two common, we'll get, after simplification, we'll get A4 XOR A2 A1. Okay, so dA4 is equal to this much. So suppose this is the AND gate and OR gate expression. Okay, so we can use this one also because this is more simplified one. Now we have to find out the KMF for dA2. So here also we'll have a 4 variable map. So we have to fill up this table with the dA2 values. Okay, so what we'll get? dA2 we have 0 1 1 0 0 1 1 0 0 0 0 1 1 0 0 1 1 0 0 0. So these are the don't care conditions. So how we can combine? So this will be one term and this will be the second term. So therefore dA2 is equal to, we'll get from this term we'll get, this is A2 A1 bar, A2 A1 bar, plus from this term we'll get, this is A8 complement into A2 bar A1, A2 bar A1. Okay, so this is the expression for dA2. Okay, now we'll find out the K map for dA1. So here also we'll have a 4 variable map. So we have to fill up this table with the values of dA1. So dA1 are the 1 0 1 0 1 0 1 0. So 1 0 1 0 1 0 1 0 1 0. Don't care, don't care, don't care, don't care, don't care. So how we can combine? So this will be one combination. So here we'll get dA1 is equal to, from this combination we'll get, this is A1 complement. Okay, so we have got the expression for dA8, dA4, dA2 and dA1. So we have got dA4, dA8 is equal to A8 A1 complement plus A4 A2. Therefore, number of AND gates required is equal to, so here we have 1 2 3 4 5 to 5. Number of OR gates required is equal to, OR gates here we have 1 gate and 2 gate. So number of XOR gate required is equal to 1. Therefore total number of gates required equal to 5 plus 2 plus 1, so it will be 8. So here we need 8 number of gates. Now let us compare these three designs to determine which one is the most efficient. So for T flip-flop we have got that total number of gates required is 5. Okay, and for JK flip-flop total number of gates required is equal to 4, and for this D flip-flop total number of gates required is 8. So D flip-flop is the inefficient one. Okay, and the most efficient one is the JK flip-flop because it requires only 4 gates. Therefore among the three designs, the BCD counter using JK. This is JK, okay? JK flip flop is the most efficient because it uses least number of gates. So here we have got that this JK flip-flop is the most efficient one because it uses the minimal number of gates, that is total 4 number of gates. Okay, so this is the most efficient one. So this is the solution of the problem number 6.19 from the chapter number 6. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.